All right, presidents, let's do some group theory. Ooh, this problem looks fun.
So actually this problem can be reduced to a graph theory problem. For each set of transpositions T, we let G sub T be the graph where each transposition in T corresponds to an edge.
Wow, that's a clever insight. Joe, maybe you're actually not that sleepy.
What are transpositions?
I know you aren't that fond of transpositions, especially on the set XXXY, but you gotta bear with me. A transposition is a special type of permutation that just switches two elements.
We will identify each generator with a special type of graph, not spanning trees. And like any proper bijection proof, we'll have to prove both directions.
So for the first direction, if G sub T isn't connected, it's simple to show via a graph walking argument that not all permutations can be generated by T. Hence, these graphs, just like Trump's smile, are out of the picture.
Note that quite conveniently, since the remaining graphs are all connected and are also given to have exactly nin-1 edges by our construction of G sub T, they can only be spanning trees of the complete graph on n vertices. This is equivalent to the other definition of trees mates, a connected graph without cycles.
Cycles? Biden, with your crippling dementia, you seem to be the type to walk in cycles.
Don't talk about cycles to me. At least my supporters don't have cycles in their family trees.
So now we'll prove by induction that any spanning trees can induce all permutations. So our base case here would be where n equals 2, where it's easy to see that there's only one possible spanning tree, and the corresponding set of transpositions only contains 1, 2. It's trivial that this set is enough to generate S2. Now on to the inductive step of the proof.
What is the inductive step?
Well, Trump, it's something like proving how day yen of your administration being dog shit implies day yen plus 1 will also be dog shit.
All right, enough banter. As for the proof, we'll first note that trees can be constructed in an inductive manner and then leverage that for the inductive step of our proof. So note that the new edge in the graph corresponds to a new transposition added to the set T, which is of the form Bn plus 1. We'll define fuss sub A of sigma to be sigma, but with n plus 1 sandwiched at position A. Our goal is to construct a sequence of transpositions in T prime that turns the identity permutation to any arbitrary permutation in S sub n plus 1.
We can apply the inductive hypothesis to assume, without loss of generality, that the permutation we start with, sigma sub 0, is the identity permutation.
Then we have three cases to consider, depending on the values of A and B. The first case is when they're equal, in which we can use the inductive hypothesis to rearrange the first n values of the permutation to what's convenient, and then apply the new transposition nb plus 1 to get the desired permutation.
The other two cases, where A is strictly less than or greater than B, are similar, except you need to alternate between applying the inductive hypothesis and the new transposition, B plus 1 twice, in order to get the desired permutation.
All right, so now the induction is finished, and we have proved that the sets of transpositions we are trying to enumerate biject to the set of spanning trees of the complete graph on n vertices. By Cayley's theorem, this number is n to the power of n minus 2.
Let's go, we solve this problem.
It was challenging, but fun. What do you guys think?
Graph theory is lame. The only graph I care about is the graph of Trump coin prices shooting up like the fireworks on my inauguration day.
A lot of results in graph theory are very useful, though, such as the Ford-Fulkerson algorithm.
When did I ever actually use that in my life, though?
Or your shenanigans with Stormy Daniels. Call that max flow min cut.